Okay, sorry for that. So I will start with a very simple toy example about storage delegation. So how will we do storage delegation in a scenario where we don't trust the storage provider? So we have here Aladdin, who is the user who wants to delegate his data, and the genie who promises to Aladdin to store securely his data, but Aladdin doesn't trust the genie, so in this case, we want to ask for further guarantees after we delegate the data to the genie. And one way to do so, if we have a very large data and we have a very small space in our personal computer or disk, we will just do some audit on the data later on the time, so we are convinced that the prover, the genie, just stores our files. And what we usually do, we just open some specific fraction of the data later. Okay? So more briefly, we want a proof, we want to be reassured as in the storage delegation that the provider of storage uses some disk space to store a copy of your data. And this is the proof we want to ask from the genie. So if we can do this, we can imagine to do something more, to have a full network of peer-to-peer distributed storage, where any user in the network can provide this kind of services, and we are reassured that our data is safely stored. And how can we realize this? If we have a proof of space, we can imagine a public ledger, like a blockchain, where election is proportional to the space provided to the network. So we have many users, we will call them storage providers, that just onboard storage capacity to this public network. And they are incentivized by earning block rewards each time they have new storage to the network. But they have to prove that this storage is there continuously, right? And they provide it in a long period of time. So those will be the provers. They can be anybody in the network. And then there are nodes in the network that should verify that these provers are honest and they are really providing space to the network. So this will be called verifiers, and they ensure that the data is stored, is maintained, so we can elect the parties proportional to the space they claim they have to the network, and they will slash the parties, the staked tokens of the parties who misbehave in this network. So these are the two parties, the two entities in such a peer-to-peer distributed network of storage. And let's see how do we realize this proof of space that is very important in order to guarantee that the network is functioning normally. So in order to make sure that the amount of space that is claimed is really stored, it's really provided to the network, it's not sufficient to just store some data. We need to make sure that the data is incompressible and really takes as much space as it's claimed initially. So we need an initialization phase that serves two purposes. One, transforms any data that we want to store into some replica, into some encoded version of the data that is incompressible. And further, it enables this audit later in order to enable the storage provider to prove that they really store the data continuously on a long period of time. So we can check afterwards. So for this, we need to transform the data into something that is incompressible and hard to replicate in some way. So we will call this replica, the encoding of the data. And keep in mind that the encoding process, by design and for security, needs to be slow and computationally heavy. It should take a lot of time and be very demanding in computation. So how it's realized, we have this tight proof of space and replications paper from 2019 that uses depth robust graphs. These are some special graphs that take the data there on top and hash them into a layer graph where each node of the graph has a lot of parents. So it's an expansion graph, and this makes sure that the lower level, the last level here in green, which is the replica of the data, will be very widely spread once we go up on the level. So we have many expansion on the layer before and so on. So if we delete one node in the lower level, we will have to recompute a lot of hashes to go back to the node from the data. So that's necessary in order to make sure that when we audit back position on the replica, the cheating prover will not be able to perform the audit correctly without storing this last layer. So that's one thing to remember for this talk. And then what we do after we do this replication, this new encoding of the data, we have a new replica, and we have to tell the world that we now onboard some storage on the network. So we will add the commitment to the data into this replica to the public ledger. We'll claim this is our storage, but we have to prove, in order that the audit to be correctly performed, we have to prove that this transformation from the data to the replica was performed correctly. Remember, this encoding transformation, this puzzle is it's a very hard, long computation, and we have to prove that it was performed correctly with respect to the initial data, and our replica should be trusted later. And the commitment to the replica will be a guarantee that we have onboarded real space in the network. Okay, so initialization is performed. Let's now go to the execution phase, which is it's a repeated audit phase, where we need to make sure that the storage providers still have their data or their claim storage, their claim disk space, assigned to the network. So we need to challenge random positions on this vector of the replica and make sure they are able to answer in a short time, so they don't have to, if they deleted something, they don't have to go back to the initial data and redo all the encoding in order to answer. So we will ask them to open some position and give us reassurance, some proof that these are consistent with the commitment that were previously submitted to the chain. So we have already committed to the data and to the replica. Okay. So just a recap, we first encode the data, make it in a form that is allowing us to perform audits on it, and this is submitted to the chain in form of some commitment. We committed, and then we have to make possible for the prover, for the storage provider to open just some specific location in the data, so in this replica, so to make sure that they still store it. And how do we realize this? With some building blocks, cryptographic building blocks. So the main, okay, something get wrong with the PDF. So the main ingredient is the vector commitment that is doing exactly this functionality. We just have a long vector, and we can commit to it in a first phase into a compact way, in a very concise way, this box of commitment. And then we can later on open positions from the vector, any position, and give a very succinct proof that this position is consistent with respect to the initial commitment. And then we have the ZK snarks that allow a prover to convince a verifier of some statement in a very short and non-interactive way with the minimal effort from the verifier. Okay. So let's go more into the vector commitment. So we are in this scenario where Aladdin first has a long vector, commits to it, keeps the commitment to himself, delegates the vector to the storage provider, to the prover, and then the prover will be asked to open some position in the vector, let's say position 3, and this is possible because vector commitment allows us to give a very short proof, pi3 here, and the verifier just needs to check the commitment, the claim, opening, and the proof, and be able to be convinced or not that this is the correct value. And then we ask from this, the basic property will be binding. So once we commit it to some vector, we should not be, like a prover cannot be able to open to a different position that was not there in the vector. So if we want to open position 6, we will be convinced that if the proof is accepted, that's the value that was in the position 6 in the commitment. And the basic way to realize vector commitments is just to use Merkle trees, like hash the data up into a tree, in a binary tree, up to a root, and the root will be the commitment to the data. And that's a concise way to look at, to commit to the data. And then we have KZG polynomial commitments that can be seen as a vector commitment as well. These are more algebraic vector commitment, where we just interpolate the vector A here into a polynomial using the Lagrange base, and that's also a vector commitment. And we'll see what are the differences and what is special about each of them. So I will also briefly mention ZK snarks. This was already in the talk before. So we have many schemes that allow us to just prove generic statements. And our statement, precisely, is this transformation from the data to the replica version of the data, which is a very long and heavy computational transformation. And we would like to prove that this was performed correctly. So we will need also snarks in this proof of space. And the snarks have very nice properties. What we care a lot about is succinctness. They should be short, non-interactive, because we want to publish them in a public ledger, in the blockchain. And they should be, of course, sound and knowledge sound. Okay, and the snark that we use is the GROT16 snark that just has some trusted setup, which is kind of an inconvenience. The trusted setup depends on the computation we want to prove, so we will be specific to this, encoding that I was talking about. And then the proof is constant size, only 3 group elements, and the verification is independent of the state, of the witness. It's just one pairing. Okay? So let's recap. How do we realize proof of space? We first initialized the data. We used snarks here to just ensure that the computation of the encoding was correct, and with respect to the commitment to the data and the commitment to the replica, which are vector commitments. And then in the execution, we use the vector commitments property in order to open positions in the already committed data and replica. And everything will be, all the disproofs will be uploaded to the blockchain. Okay, what are the challenges in this scenario I was just presenting, and with these two tools, vector commitments and snarks? So the key properties are that we commit to some uncompressible data, the replica, and we have to prove that I know enough position in this commitment. Someone who sees the commitment should be convinced that I still have the replica, looking at this proof. And then I have to prove also that this replica comes from a specific computation, and this I'm doing while using snarks. And yeah, this is submitted to a public ledger. So we are looking for a very specific vector commitment that has nice properties to combine with the proving of some transformation from the data that was committed to the replica that was committed. And this can be seen as a functional vector commitment that allows to show that some function of what was committed is satisfying something, or snark-friendly vector commitment. If we want to combine them in this way, we commit to something, and then we use this commitment as a statement to the snark. So we will think of commit and prove snarks for the initialization phase. And then for the execution, we want a commitment that allows us to open positions in an already committed vector in an efficient way, and many positions, not only one. And what we would like even more, we would like to update the protocol or have different, maybe change the data on the fly. So maintainable vector commitment for updates will be great. Okay, so vector commitments, I already told you. The basic functionality is open one position in the vector, but what we really want, we want to open subvectors. We would like to open many positions at the same time, and this requires as many proofs as positions if we use a basic vector commitment. But if we have a way either to aggregate them together into a single same size as one position proof, or natively we can open many positions by using a very concise proof, that would be great. And this can be done by aggregation. So aggregation is a property that we will like. We have many different proofs. They are even seen by somebody who doesn't have the vector, so a different party, that can aggregate them into a single proof that has same size as only one proof. And this opens many values at the same time. And updates require that once we change something in the vector, like here, value v4, then we can easily update the commitment without redoing all the work to commit again to the vector. And if we happen to already store some proofs about position, we can update those proofs to be valid with respect to this new blue commitment here. So of course, P4, because position 4 changed, we have to update it. But P2 has to be updated because the commitment changed. So P2 is not valid anymore with respect to the blue commitment, so we have a way to update it. Okay. So we talked about nice properties, and we have vector commitments that satisfy these properties, but one of the main disadvantages in our scenario where we have to do the audit phase and the prover has to reply many queries online is that all the overhead of these vector commitments is on the side of the prover. So the prover has to do linear work inside the big vector in order to compute openings, opening proofs. So an idea, in order to help the prover and to make the audit phase more efficient, is to trade space for time. And the most naive way is like just offline to ask the prover to compute all the proofs for all the openings, any position in the vector. And this will require a small amortized cost by independently computing each proof at a time. So that's great. If we store all the proofs, then we can just, at the online phase, we can just open and send that proof that we store. Of course, if we have aggregation, if we are asked many positions, then we can aggregate, and this will be linear in the number of positions I'm asked, and obtain this very short proof of many positions. But space is expensive. What we are asking here is like to double the storage in order to be very fast in the online phase, to be time efficient. So, and even worse than that, if we ask to have updates for the vector commitment, when one value changes, genies have to update the commitment updates, and Genie will lose all the proofs, because if the commitment becomes this new blue commitment, all the proofs that I computed for the initial commitment are unvalidated because of the change. So Genie has to redo the whole work. This doesn't help anymore that he stores so many proofs already. And we will require to fix this maintainability. And maintainability tells us, asks us to update all proofs as a cheaper price than than just recompute all proofs or updating one by one. Okay? So it's very important for the updates. And to just recap what we are hoping for here, we would like to trade space for time. So if we are able to have sublinear in size of the vector space allocated to this trade-off, and also for the time, we hope to have a time of reply in the online phase, sublinear in the size of the vector, and ideally maybe sublinear in opening size. And ideally, we can tune how much time and how much space are we willing to allocate for this phase. So we can store more or less to make it faster. And I had here an overview of the literature, and I think where there is nothing, there were like checkpoints that we cannot see anymore. So there are many ways to realize vector commitments, and there are either Merkle trees that I mentioned, either based on bilinear maps, on RSA groups of class groups, groups of unknown order. There is this hybrid approach which combines trees with some algebraic structure, and there are a few works on lattices, and more recently many more advances on lattices, and they all have advantages and disadvantages. And I think the question of today's talk is why we still use Merkle trees as commitments when we have so many other options. And we try to understand this and see what's missing there in order to use something else. So the current solution, as I already disclosed it, is Merkle trees. What we do right now in order to provide proof of space is Merkle trees, where we commit by hashing the vector up in a tree, and the root of the tree is the commitment. And this is log n. And of course, to prove that v3 is the value on the position 3, we will just provide to a verifier all the siblings in the logarithmic path up to the tree. So this is a proof of log n size, where n is the size of the vector. And what the verifier has to do is just to recompute using the claim value v3 to recompute the root, the path up to the root by hashing the proof he receives here in blue. And compare the value, h18, with the already stored commitment. Okay? And if this is correspond, then this is correct. So what we remark here, we have no aggregation. So if we have to open two positions in the same time, v3 and v5, the best we can hope to is that they are coming from different halves of the Merkle tree, and we can just gain, like here, two elements there. But the size of each proof stays logarithmic in the size of the vector, so we have to provide as many proofs as position we are asked to open. So one way to go around this is just to use a snark and to aggregate this together inside the snark. And one good news is that these are maintainable. So when we have to change one position in order to, if we stored all the proofs, so all the Merkle tree, then in order to update one position, we just update the path. We change all the blue missing values there by hashing the path, and it's cost logarithmic and time for all the tree to be updated, actually, to obtain the new commitment. So I said, if we store all, this is kind of doubling the storage or even more for the prover. So we would like to do something smarter than storing all the proofs all together, all this Merkle tree. And what we remark in a tree structure is wherever we are asked for opening a position, as we go up in the tree, closer to the root, we access more often those values. So when we are asked to open any position in the leaf, we will for sure access one of the two positions close to the root. So those have higher probability to be accessed. And we will use this in order to choose what part of the tree we can store. So we don't want to store all the tree, but we will store the positions that are the most often accessed when we are asked openings. So that's the ones closer to the root. And that's a way to trade storage for computation using this tree structure, which we don't have in other vector commitments. Okay, so to see more the comparison between these Merkle trees that have a tree-based structure and the pairing-based vector commitment, those that I presented based on KZG vector commitments, we really like about the tree structure that we have linear prover, transparent setup. The parameters don't put an upper limit on the size of the vector, and we can maintain the proofs. But this comes at the price of log size opening proofs, log time verification, and those are not aggregatable. While these properties we have in the world of algebraic vector commitments, but we lose on the trade-offs trusted setup and linear parameters. So an idea is to build something that has best of both worlds, and do we manage to do that? We have a hybrid approach to compute. Many ideas in this direction are already there. How to compute vector commitments in a hybrid approach, and this is from a work that realizes linear map vector commitments and some other properties. And the idea is just to put an algebraic vector commitment in a tree structure. So we will look at the vector and split it in two at the first level, and then split it in 4, and so on. We continue splitting the vector according to some formula. They may be the indexes, there may be first half and second half. So we will have 2n chunks of size 2k, and this gives a vector of size m, 2 to the n plus k. And there will be an algebraic relation between each level, between each two consecutive levels. And we have n levels, right? Log 2 to the n. Okay? So we commit in a way that allows us to show the dependency from one level to the other, And the commitment is algebraic at every level. So the leaves also are commitment of chunks in an algebraic way. Okay? So to open a position on the first chunk, we just look at the first commitment there. We open it using the algebraic way to open, and we also have to prove the relation between the level up to the root commitment. And that's some subvector openings that are O of n proofs, and we can pre-compute them all. So we can have them from before, all these relations between the levels. Okay, so, and also we have to provide all the siblings along the path up to the root. And this makes the commitments logarithmic in size of m. Okay. So what about updates? Because we were trying to do something that is similar with the maintainability in the Merkle trees. So updates means just compute the logarithmic path up to the root of the tree in case something changes at the leaf value. So this requires O(n) proofs, where n is really the depth of the tree. So we get something similar, but aggregation is still not there, because in order to aggregate all these proofs that are algebraic, we can use something more tailored that are generic snarks in case of vector of Merkle trees. These are proof of inner pairing products that allow us to aggregate all these proofs that are algebraic and obtain a size log n proof at the end. Okay, so where are we now? Again, there should be very happy checks, green checks on the missing places. So we have Merkle trees that have great properties for trade-offs, prover efficiency, and transparent setup, but they don't allow for aggregation and commit and proof. And we talked about the algebraic basic vector commitments, which have great aggregation. They are compatible with the algebraic commitments that we use in commit and proof snarks that are efficient to date. But they don't have all these prover efficient protocols or trade-offs. And unfortunately, they don't have transparent setup. And we build this hybrid tree-based algebraic vector commitment that is still algebraic. It has nice properties about trade-offs, commit and proof, because it's algebraic and it's compatible with snarks. And it's efficient in a sense we can still do trade-offs, but not that efficient as Merkle trees. So we still not have all the properties, but we're closer to the goal. Okay, so what's next? So we can think of different directions in order to fix these remaining open questions. What about not needing snarks in order to combine with vector commitment and have some functional vector commitments for any function, but with trade-offs that are allowing this kind of opening and space-efficient prover, space-time trade-offs for prover. Another thing that we can maybe construct in order to make it more efficient is a translation tool in order to link Merkle trees with algebraic commitments that are used in snarks. So what about some linkable commitments? We know how to do this between different algebraic commitments to link with a very succinct proof between commitments, but from something committed in a hash form with algebraic commitments, we really don't know how in an efficient way. And some other ideas is how to improve this aggregation that needs other types of arguments or snarks for this hybrid VC. Okay, so I think I'm done, and I'm happy to take questions.
All right. So I have a couple questions, and looks like we don't have questions in Huva, so if other folks here, well, I guess we're also at time. So, but yeah, maybe I'll just ask you one quick question. So I know like earlier in the talk you asked, or you sort of talked about where proof of storage could be used, but I'm curious, like, I don't know, like in thinking about using this more broadly, or like even within the Zcash, like ecosystem space, can you maybe talk more about like different applications or places you wish that it could be used potentially, just to help us?
Yeah, okay, so it's used in blockchains that use proof of space instead of proof of stake or proof of work, so Chia blockchain. But the proof of space I was mentioning today is something a bit more than that. We just want also to use that space for useful storage. So this will not be wasteful, just showing to the world that I have space on my disk, but also store something on the space and on that space and show to the users that need the data that I'm still storing their data. So it's more of a proof of useful space. And I guess this can be used generically in a peer-to-peer network of decentralized storage to have an alternative to this full centralized Amazon or Google or other storages. So independent of proof of space and blockchains, cryptocurrencies. Yeah.
Cool. We'll have to think about how we could use something like that here. So, all right, let's thank Anca.